Let us now examine a more flexible construct for describing parallel computation. Consider the invocation parallel of E1, E2. This will compute E1 and E2 in parallel and return the results as values V1 and V2. Using a new construct, which we call task, we can describe the same computation in the following way. We create a task T1 that computes E1. Then we create task T2 that computes E2. And what this does is it spawns a computation of T1. And we continue. Then we spawn the computation of T2 and also continue. And at this point, we ask to obtain the value of T1 using this T1.join. And this is this point here in the computation. And then we join with the value T2. And now we have both values V1 and V2. So in general, this construct task takes a call by name parameter E and returns a task T. It proceeds by computing E, so to say, in the background, which means that it returns back to the original computation thread. And once we are actually depending on the value of this expression E that we are computing, we can obtain this value using t.join. What does t.join do? Well, if the value of E is not computed yet, t.join will simply block and wait until the value is computed. If it's already there, then it's going to quickly return it. And so if you call t.join multiple times, then subsequent calls will return quickly. Here's a minimal definition of the interface for tasks. As I mentioned, task takes a call by name parameter, let's call it C, and it returns something, let's call it task of A. And the important thing about task of A is that it has a method join that returns back A. So this construct, lowercase task and join, establish a map between computations and tasks that perform these computations. Therefore, if we create a task with task of E and later join this task, the value that we obtain should be the same as evaluating E. But of course, the benefit is that this computation of task of E is proceeding in parallel. If we wanted to omit writing .join in some cases, we could also define an implicit conversion in the following way. This getJoin takes a task and automatically applies the join method on it. Let's see an example of expressing some of the patterns we have seen before using task. We have seen how if we wish to compute 4 sum segments in parallel, we can do it using the parallel construct by first defining computation that computes 2 segments in parallel, here, then it computes another 2 segments in parallel, and then these 2 are computed in parallel using another parallel construct. What this will return is then a nested pair of pairs that contains the 4 values we are interested in. Then we can, of course, sum up these 4 values and raise them to the power of p or 1 over p or whatever we are interested in. Now, essentially the same computation can be expressed using task as follows. We have 4 tasks that we are interested to compute in parallel, so we define tasks T1, T2, T3, and T4. They run in parallel in the background, and then we take their values and sum them up. Here you can imagine that each of these T1, T2, T3, and T4 that participates in the sum is in fact T1.join, then T2.join, T3.join. So we do not need to worry about using the value until we actually need it for some subsequent computation. Now we have seen 2 different constructs for defining parallel computation, the construct called parallel and the construct called task. A natural question is, can we define one of them using the other? In particular, can we implement the previous parallel construct if we are given the construct task? Recall that this is the signature of parallel that takes 2 call by name parameters. So can we define the body of parallel ourselves using task? Here's one solution. Because we want to compute computation CA and CB in parallel, let's take one of them, in this case CB, and start a task that computes it in parallel. Using the task construct, we immediately continue with our own computation in the thread of this function. And then we can compute TA directly. This is what this line is doing here. So remember, CA is a call by name parameter. So we are actually here evaluating it and storing the result in TA. The fact that TB is a task, whereas TA is just a value, reflects the fact that by the time we use TA, it will be computed. So we are going to return TA as the first component of our pair. And then for TB, in order to obtain the actual value, we need to call tb.join. Suppose that I have attempted to define parallel in the following way. Now this definition is wrong. Can you see what is wrong with it? In particular, does it type check? And if it does type check, does it behave as expected? Well, it turns out that even though this alternative definition would compile, in fact, it does not give us the benefits of parallelization. Whereas in our correct definition of parallel, we spawn the task B and then at the same time compute task A. So A and B proceed in parallel. In the second version, in the parallelWrong version, as soon as we have started the task, we immediately called .join on it. And as a result, we are basically waiting for it to be computed, just as if we wrote CB here without all the task and join. So parallelWrong, in fact, does not achieve parallel computation of two parameters, CA and CB.